Welcome back to ENAE 788M, Hands-on Autonomous Aerial Robotics. In this lecture, we'll talk about the fundamentals of image processing. So recently we have talked about the GMM, how the color images are generated using weird pattern and all. Let's talk about more fundamental about how the images are processed, right? So what do you think an image processing is? So let's say you have an image, right? What you want to do is you are trying to alter this image using some function or some task. For example, your image one was initially the shown in the figure. Let's say it's I1, and you apply some function phi, and you get this image I2. Like, it can be anything. In this case, it's converting the RGB or the colored image to the grayscale image. And in this case, we have seen that from the grayscale image, it's trying to detect the edges of the gates that we are seeing. And the third task, it's refining those gates. So our quadrotor basically can go through these gates. So you can also simply process the images using color thresholding. So for example, you had this scenario, right? In the final project, you will have the multiple different color gates. Let's say one is green, one is magenta, and one is red. So you can simply do a color thresholding that, okay, I'm gonna just select the green scale here or the green color here. Next, you'll say I'll just gonna detect the pink here. I don't get anything else. And then I'm just gonna focus on my red parts of the image. So using this, you can definitely, using the standard color thresholding, you can definitely detect different kind of thing. But in real world, these most likely won't work because you will have different sort of reflection, different sort of contrast, depend on the time of the day and the lighting condition and a lot of things, right? So in your final project, we'll highly recommend, or actually in the next project, we'll highly recommend you to use Gaussian mixer model to detect these gates. So moving on, so you have an image like this, right? So if you see in this image, I choose a pattern. I choose a block. This block is made up of 3 channels, right? Red, green, and blue, like we discussed in the weird pattern thing. So in the red channel, I have some value which is in this case going from 0 to 1. Same with green channel, same with blue channel. So combining all these 3 channels, I get one colored image, right? Now, if you recall the bear pattern, you see in this that you see this black square blob, right? These blob have this blob is basically 1 pixel, and this blob has 2 green elements and 1 blue and 1 red. These are the filters which only pass red, green, and blue light respectively. So this is what we call a 1 pixel, right? So this 1 pixel on your image shows these values. So let's say this 1 pixel in this case has 0.112 in red channel, 0.342 in green channel, and 0.689 in blue channel. So notice that these values, in these matrices that you're seeing, they are normalized between 0 and 1. But these can be also 8-bit, 16-bit, and 24-bit. 8-bit would be the most common for you during this course because you don't want to have a heavy sort of thresholding on memory on embedded devices, and 8-bit processing images are good enough for the task we'll be doing in Windows. So rather than going from 0 to 1, they will be going from 0 to 255. So there's one more important thing to note here is that if you're using MATLAB, and if you're, let's say your red channel has value of 240 and you add 20 to that value, it will become 255 in the image space, right? In the red channel, it won't exceed 255 because that's the maximum limit. If you are dealing with NumPy or Python, and if you're doing such operations in Python that you want to add 20 to 240, then what Python is going to do is after 255, it'll reset it to 0. So what your value of 240 plus 20, it'll give you 5. So be sure that you are not having a problem with that when you are printing values, right? So there's a thing called point operators. So point operator, what it does is Like let's say you have one particular pixel right here, right? You apply a function that only and only changes the value of that particular pixel. It doesn't matter what the neighboring pixels are. So in this case, I'm trying to threshold pink. So I want to remove the pink background from this image. So see, I was able to clearly identify where this keyhole mountain or arch is, right? So moving on. So, but there's a catch. To detect certain important things, or commonly called as features in an image, we cannot just rely on the point features alone, because definitely neighboring pixel would give us extra benefits, right? So we need to rely on the neighboring pixels of the points as well by multiplying the image with a matrix or a kernel. So, but before diving into the kernels, let's try to understand what are features in an image, or what are features in generally machine vision that we call commonly, right? So is it similar to what a human visual perception is? So this question has some debatable answers and can be very different, but one thing is for certain, that feature detection is the fundamental building block for a variety of computer vision applications. So applications like panorama stitching that we find in our smartphone or in Adobe Photoshop, these heavily rely on these features. So your phone take multiple snapshots of the surrounding and stitch a big panorama image, for example, right? So they do it based on these features. So coming back to the question, what are features? So it's a piece of information which is relevant for solving a computation task. It can be specific structures in the image, such as points, edges, or objects. Can be planes, blobs, anything else, right? So can you think a few types of features? So certain locations in the images, like corner of the building or mountain peaks, can be considered as features. So these kinds of localized features are known as corners or key points or interest points, and are widely used in different applications. So these are the characteristics by the appearance of neighborhood pixel surrounding the point or local patches. So in this image that you see, you have local patches here, here, and you have some small local patches, and you have local patches here, 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 here. Right? The red local patches that you see are called strong features, because they most likely would be unique in the next frame. So we call good features which are generally more sharp, or they have the high frequency characteristics or things like that. Whereas your weak feature, the things denoted in black, are basically weak because they don't have any pattern change, or they don't have a very high frequency things, or they are repeatable. For example, if I consider this block and this block, right? If I want to match these features, that are these two features the same? My answer would be most likely yes, because most of them are representing the same color of gray, right? I cannot distinguish between this feature and this feature. So there are multiple ways to detect good features. One of them is called convolution. Have you ever heard of a convolution neural network? Like, what is convolution? So people have been trying to use AI in general, like artificial intelligence, right? So they are based on these convolutional neural networks. So convolution is that important right now that almost every AI system that does some sort of image processing is relying on the convolutions. So what is convolution? Let's try to understand that. Right? So right now, think of it as an operation of changing the pixel values to a new set of values which are based on the values of the nearby pixels. So if you don't understand that, don't worry about it, because we are going to go much deep into it. So convolution is an operation between two functions, let's say f and g, which results in another function which is depicting that how the shape of the first function is modified by the second function. So the convolution of two functions, say f and g, is written as f star g or f convolution g, and is defined as integral of minus infinity to infinity f of tau g of t minus tau d tau. And you can also replace this as integral of minus infinity to infinity f of t minus tau into g of tau d tau. So this equation you're saying is called the convolution theorem, that you can just replace minus tau from g and you can put it to f and vice versa, right? So let's try to visualize the convolution in one dimension. So the following figure depicts that the convolution is in black of the two functions which are denoted by blue and red. So one can think the convolution as the common area under the curve of the function f and g. So you see in this that there are two functions. So this blue function is one function, the red function another function, and when they are basically colliding or basically have a common area, when one function slides over the other from minus infinity to infinity, you get this black curve, right? So this is what your convolution of f and g would be. So just like 1D convolution, one can also compute a 2D convolution. So note that the size and the values of the kernels may vary. Like in this, you have a kernel of 3 cross 3, right? So the values and the size of these kernels may vary, which will eventually change the output. So these convolutions are most commonly used operation for smoothing and sharpening tasks, right? So you have an input image, right? You pass through a kernel, which you will have a matrix multiplication or a convolution in this case, and you get a desired output. Okay, so one more important thing to note is if I want to convolve at the pixel 7, right? So I want the neighboring pixel 6, 4, 6 and neighboring set of pixel in this axis, right? But since my image has one edge, so 7, this point is the cornermost point. So what I do to convolve these images, let's say my kernel size is 3 cross 3, right? So I need a 3 cross 3 here as well. So what I do is I pad this image at the corners. So I pad this image, I have certain values, like I can put 0 or some padding. So my image is extended by n pixels basically, and then I try to convolve that. Okay, so let's talk about blurring, like how we can use blurring, how we can blur an image using convolution, right? So this example shows that you have a kernel, which is basically you have a 3 cross 3 kernel, and you have at each element you have 1 by 9, 1 by 9, 1 by 9. So basically you are trying to smoothen it out, or you were trying to blur that image. So each of this 1 by 9 will be corresponding to whatever your image is, and finally you get some output. So note that the sum of the mass or the kernel is 1 again, as you saw in the last slide as well, right? So it is very common to also choose the value 1 or sometimes maybe 0, that depending on what your type of operation is. So think about it, why is it 1 or why is it chosen to be 0, and then we'll discuss in the class. Okay, so more convolution operations. So let's talk about convolution, identity convolution, which will basically, if I convolve this this matrix by my input image, that will give me an output image exactly the same as the input image, right? That's why it's called identity. Next is sharpening. If I have something like this, like the higher value in the middle and -1 in the 4 quadrants, I'll have a much sharper image if I compare with the original image. Next is a Gaussian blur, or next is the normalization, or commonly known as box blur as well. So just like the case we discussed in the previous slide where everything was 1 by 9, this is exactly the same representation, which with 1 by 9 as a common factor outside and 1 1 1 1 being the neatest, right? So the next part is a 3 cross 3 Gaussian blur. So again, I have a normalization factor. If you see D, E, and F, I have some normalization factor because my matrix has some higher values, right? I don't want to increase the intensity of whatever my image is, right? If I don't have this 1 by 16, my image will brighten at multiple scales. So in this, I have a Gaussian blur. Again, the higher value, when I'm talking about blur, my middle element, if you consider these two, my middle element will have a higher value than the adjacent values. Okay. and these would be negative. If I want to sharpen this image, I will have something like -2, -2, -2, -2. Again, rather than having a 3x3, we can also have a 5x5 Gaussian blur, and you can actually compare and see the difference between the two blurs. Right now, I have unsharp mask. Again, now you can see that my middle value, because I want to unsharpen this, it is exactly the opposite of that guy. So in the middle value, I have -146, and these values are so note that the denominator in all these cases, whatever I have outside, all the matrices are used to normalize. Okay, so let's talk about the finding the edges. So apart from the smoothing operation, convolutions can also be used to detect features such as edges as well. So the figure here given below shows that how different kernels can so the figure here below shows how different kernel can be used to find the edges in an image using convolution. So go back and notice how these operators are different from the previous ones. Deconvolution, right? So clearly, as the name suggests, deconvolution is simply a process that reverses the effects of convolution on a given information. So deconvolution is implemented generally by computing the Fourier transform of the signal h and the transfer function g, where you can say that my h equals f convolution g. In frequency domain, we can, if we are assuming no noise, we can write that my f equals h by g. So it can also be used, it can be used for deblurring and image restoring task. So in this, you can see my input was a little bit blurry, right? If I do a deconvolution operation on this, I can see that clearly, the image clearly. So let's move on to correlation. So convolution is a mathematical operation on two functions that basically produces a third function, which expresses how the shape of one is modified by the another, right? Another measure that is commonly used in mathematics and in signal processing in general is called correlation. So correlation is a measure of similarity of two series as a function of displacement of one relative to the another. So this is sometimes also called as sliding dot product or sliding inner product. So the equation is given by f star g is equal to -infinity by infinity f conjugate tau g t plus tau d tau, and can also be, there must be an equal to here, I skipped it, is equal to -infinity to infinity f of tau t minus tau g tau, right? So f is the complex conjugate here, because we are talking about the Fourier domain, right? So let's try to understand how these things look like. So you have a function f and you have a function g, right? We are trying to find the correlation between these two functions. So you will get a correlation output, something like this. This is also known as cross correlation, because you are trying to correlate between two functions. If it would have been correlation of that function f with itself, it's called autocorrelation. So you can see the comparison of cross correlation and convolution, right? So coming back to autocorrelation that we discussed, so you have a sine wave, right? And you have another sine wave. We are trying, you have the sine wave and this sine wave are exactly the same. That's why it's called the autocorrelation. So autocorrelation is basically of a signal is basically the correlation with its delayed copy. So it's commonly used tool in signal processing to find the repeating pattern in a periodic signal. So in this example, you can see that this signal xt was fixed, and the same signal basically comes and projects itself to the same signal from infinity and goes back to the opposite spectrum of the infinity. RT here is the autocorrelated output that you can see. So this is a visual comparison, right? You can see that you have two functions f and g, right? In all the three cases, you have convolution and you are trying to convolve f star g, right? And you are trying to convolve g star f. So here f is being the kernel for g, right? Similarly, for cross correlation, you have g cross g star f and f star g, and you can see you can, and in autocorrelation you have obviously you have f star f and g star g because you are doing an autocorrelation, right? So note that the g star f and f star g of convolution and cross correlation are giving you the same output. So let's move on to Fourier transforms. So if you don't have any idea about what a Fourier transform is in general, so I would highly recommend you to go to this link. So this is a video by 3 Blue 1 Brown about the Fourier transform. Please watch it, or if you don't know Fourier transform, please watch it and continue this. So the Fourier transform is an important tool used in image processing to decompose an image into its sine and cosine components. So the output of the transformation represents the image in the Fourier or frequency domain. So while the input image is the spatial equivalent. Right? So in this Fourier domain image, each point represents a particular frequency which is present in the spatial domain image. So you have certain set of points here, right? So this represent one R and G and B channel in this. In the frequency domain, you have each point representing one particular frequency. So there's a thing called FFT, which is called the fast Fourier transform, which is basically an efficient way to transform into Fourier domain. So the standard Fourier transformation was a relatively slower, and this is much more efficient way. And if you are gonna use this, if you wanna do a Fourier transform, please use FFT in Python, and you can call NumPy function for that. So the Fourier transform is used if we want to access the geometric characteristics of a spatial domain image. So because the image is in Fourier domain, because the image in the Fourier domain is decomposed into its sinusoidal components, it is easy to examine or process certain frequencies of the image, so thus influencing the geometric structure in the spatial domain. So if you directly try to plot the output of the Fourier domain, you will find the image like this with most high frequencies at the corner of the image. So you see in this image that you did a Fourier transform of this guy. If you don't do any shifting, like forget about this for a moment, if you don't do any shifting, you will have high frequency on these four corners of the image, right? So what people do is people do an FFT shift, basically shifting in the frequency domain. So we basically rearrange the Fourier transform output by shifting the zero frequencies component to the center of the array. So basically you are projecting this. Think of this as folding this part here, folding this part here, folding this part here, and folding this part here. Okay, and basically doing FFT shift, you will get an output like this. Okay, now you can basically see that this part is focused on very high frequency because the intensity value, which is white in this case, almost white, has the highest frequency. Okay, so you can use basically FFT shift function in MATLAB, and you can also call numpy.fft.fft shift in Python. So the beauty of FFT is, even if you don't have any idea how bad or at what angle the image is rotated by, right, and you want to you're trying to find that image, or you want to derotate that image, what you can do is do an FFT operation, and this would be the output of your image. So note that in the previous one, when the image wasn't rotated, it was erect, you were getting the axis at these two perpendicular lines, right? When it's rotated at exactly 45, you will have things like this. So you can use these information to derotate the image. So now we have a noisy image, right? The one you can see here. So in this noisy image, we can say that we added a salt and pepper noise, which is basically high frequency noise, which adds a very high frequency or very unused sort of So now we have a high frequency noise data. So it took this image, like the original image here, and we added high frequency noise to it. In this case, it's a specific salt and pepper noise, which is one of the high frequency noise, which you can read about it. So in this image, I want to remove the amount of noise or amount of high frequency noise here, right? So what I do is I take an F50 and I do an F50 shift. So now I have this data. This is the F50 data, right? This is the output. So this axis and this axis, right? So this is the real axis of my Fourier, and this is the imaginary axis of my Fourier, right? So, and this represents the frequency, right? So if I talk about my high frequency data, it'll be this region, this region, this region, and this region. So I want to remove all these frequencies, right? So what I'm gonna do is to remove all these 4 quadrants, I will basically just remove these frequencies, and then I basically project my frequency or Fourier data back to the spatial domain, and I'll get something like this. So notice that this data is more blurred, but most of the noise that we had in the salt and pepper in my original image is gone, right? So I will highly recommend you to play with F50 in general over a certain set of images, and how you can use these operations to perform different tasks like deblurring, recovering from noise, and things like that. So start with OpenCV, start with these functions, try to do color thresholding, maybe things like that. Get familiar with how an image processing toolbox or how an image processing in general works.